very much, Lorenzo, and thank you very much to the Simons Foundation for having such a lecture series, and I'm very honored to be part of it. So today I'm going to try to give you a broad overview of some of the challenges and issues facing us as we try to make regional climate projections for the coming decades over North America. So this will be a broad talk aimed at, I think, the non-climate scientists in the audience, and I hope I can be successful. So I just thought I would let you know where I spend my time. This is the National Center for Atmospheric Research in Boulder, Colorado. And this is a beautiful building designed by I.M. Pei. And in the background, we have our own flat iron, not a building, but climbing rocks for people when we're not working. NCAR is an NSF-funded organization devoted to atmospheric sciences and more generally climate science. And we serve as a resource, I would say, for the university community, the university atmospheric science departments, to enable the larger community to undertake projects that would be too big for any single department. So, for example, we have aircraft that fly to sample air samples around the world. And then we also build a climate model, one of the leading models in the world. And this is all done with university participation. And so the NCAR scientists sort of serve as focal points to coordinate this activity. So the most important thing, as Lorenzo alluded to in his introduction for me, is this concept of, I'll put it in the terms forced and free climate variability. And these are two very distinct aspects of climate variability. And by forced, we mean climate change that you can attribute to external factors. For example, the rise in greenhouse gases, aerosols from volcanoes, other factors that we consider external to the climate system. And then by free variations, these are internally generated, spontaneously generated variability in the climate system. And to appreciate the difficulties in making projections of future climate, we really have to understand these two aspects of climate variability. So let me just give a broad brush view of some of the main forcing agents that change the disposition of incoming radiation for our planet. So of course, a big factor would be changes in solar output. So for example, the 11-year sunspot cycle will change the amount of incoming solar radiation. And then, of course, orbital changes will affect the amount of radiation on Earth. And then another big factor that is natural in origin are volcanic eruptions, and these spew large amounts of aerosols into the atmosphere, and they're lofted high enough that they can actually have a substantial cooling effect on the planet for several years. This is an image of an explosion in Russia in 2009. So these are what we consider the natural external radiative forcings for our climate system, two of the main ones. Then on the flip side, we can think of the anthropogenic external forcing factors. And again, just giving you two main examples here. On the left are the latest updated curve of CO2. And I just realized that this record is now about as old as I am. And it started in, I think, the late 1950s. And we've now witnessed an increase of something like 25 or 30%, an increase in the concentration of CO2 over the past 50 years. So this, of course, is the very important factor affecting climate. And then on the right, another main anthropogenic factor would be burning of coal and other materials that produce sulfate aerosols that then can lead to a cooling of the planet. So these are the main sources of externally forced climate variability. Then on the free side of climate variability, again, these are due to processes that are internal to the physical climate system. And so these may be due to atmospheric processes, oceanic processes, and then interactions among these different parts of the climate system. So I'll just give you some broad brush examples of variability that results just from the stochastic, nonlinear nature of these fluids. So the atmosphere is obviously a very variable and sort of fluctuating medium on very fast timescales, on the order of days and weeks, and is responsible for much of our weather in the temperate latitudes. And so on the right is an example, for example, undulations of the jet stream, which are derived from instabilities of the flow. And these are important sources of variability in the atmospheric flow patterns, which can then affect climate. And I will go into more detail on that. Then, on the other hand, we can think of the oceans, another fluid. And this, of course, because of its large thermal inertia, the typical timescales of variability in the ocean currents and the ocean temperatures are more on the order of months to centuries. And for example, the upper ocean, the upper part of the ocean, which is in contact with the atmosphere, has timescales on the order of months. And then, of course, the deeper ocean circulation is more slowly varying. And a prime example of oceanic variations intrinsic to the ocean are changes in the so-called conveyor belt, which some of you may have know the terminology. This is a global circulation that is driven by density and density currents due to changes in temperatures and salt. And this brings warm salty waters northward in the North Atlantic Ocean. They cool at high latitudes, and then the return flow at depth brings the water back down through the Atlantic. So not only do the atmosphere and the ocean have their own intrinsic variability, then we have a whole new class of phenomena that derive from the coupling between these two components. And when there are strong interactions between them, we get variability on sort of years to decades. And a prime example, of course, is the El Nino phenomenon, which affects much of North American climate, particularly in the wintertime and the springtime, from year to year. And this is a phenomenon that originates in the tropical Pacific Ocean atmosphere system, but can have global ramifications through teleconnections in the atmosphere. And then another prime example of a structure of variability that derives from the coupling between the ocean and the atmosphere is the so-called Pacific Decadal oscillation in quotes. And this, again, is a phenomenon that affects, especially places in western North America, affects our precipitation and temperatures from one decade to the next. So let me just give you some examples then of the primary climate variability phenomena that occur on these multi-decadal timescales. So on the left we have, as I said before, the Atlantic thermohaline circulation, this sort of near global ocean circulation. And I have a record here on the lower left of the temperatures in the North Atlantic that are sort of a marker, signature of this thermohaline circulation. Our records go back roughly 100 years with reliability. And here, the blues and the reds are indicating if we have colder or warmer than the long-term average ocean temperatures in the North Atlantic. And you can see very much, very marked signature of this decadal variability. And then on the right side is the temperatures in the tropical Pacific Ocean associated with the specific decadal variability. And again, you see remarkable persistence of warm and cold epochs that span decades. So these are the kinds of phenomena that are happening regardless of whether we have an increase in the greenhouse gases, whether we have changes in the solar irradiance, or whether we have changes in volcanic eruptions. We will always see this variability because this is produced spontaneously by the physical climate system. So one very important concept to really appreciate how important the free climate variability is a concept termed climate noise or weather noise. And so in a nutshell, this arises from a short timescale process, but you can have sampling fluctuations that then carry over the variability to longer timescales. So for example, a very simple model for atmospheric mid-latitude jet stream variability would be a first-order Markov process with driven by some Gaussian white noise forcing and then a little bit of persistence in the system. And what we find for typical atmospheric conditions in this region of the jet stream is something like a 10-day e-folding time for variability of the jet stream. So you would think that there can be then there is no memory. The processes within the atmosphere don't actually lead to variability on longer timescales. However, because this has a spectral character that has variability on all timescales, the sampling fluctuations associated with such a process gives rise to variability on all timescales. And I will show you that that's actually a very important factor in leading to some of our uncertainty in our projections for future climate in the coming decades. So then schematically, we can think of the free side of climate variability as being some Markov process. It could be multivariate red noise or just a simple single Markov process. And we have variability, and this can, the fluctuations can occur on a broad continuum of timescales, let's just say between 1 and 50 years, just nominally. And then superimposed on this free climate variability is the signature of the forced component of climate change. And this is due to the slow buildup of greenhouse gases, changes in solar irradiance, changes in volcanic activity, and the like. And so you can see the dilemma here that we're faced with. If the free climate variability has timescales that are long, i.e. multi-decadal, and we're trying to examine either the impact of the forcing on the climate system or trying to attribute past climate changes to some external agent, it's actually very difficult when we're looking at just an order of 5 decades or so, because the two signals can often have very similar amplitudes. So if you're sampling this part of the record, you know, you might, and this is a temperature record, you might be inclined to dismiss any impact of greenhouse gas increases. Whereas if you're in this part of the record, you might think you have very strong signature of externally forced climate change. And of course, both of those interpretations would be flawed, because one really has to take into account the free climate variability. Okay. So to summarize, and then I'll get into actually showing you some projections for the future, we can think of climate change as being made up of a change in the sort of the mean of two distributions, and this would be attributable to a change in the external forcing, radiative forcing. And then we have some uncertainty in this distribution, or some spread of the distributions, and this is due to the free component of climate variability. And of course, to distinguish the signal from the noise, we want to have large signal to noise ratios. And this can be either if the signal is large or the noise is small, or both. And I think what I hope to convince you of today is the next 50 years we're kind of in the twilight zone where we have neither, they're on the same footing, the forced climate change signal and the free climate variability, at least as it pertains to North American climate. Okay, so how do we go about making our projections for climate in the coming decades? So of course we base our projections on comprehensive numerical models of the climate system, and these are largely based on the equations of fluid flow and thermodynamics, conservation of energy, etc. And so typically our numerical models of the climate system typically contain these 4 components, although we're now adding additional representations, for example, for land ice, for biogeochemical cycles, etc. For the models that I'll be talking about today, they're made up of these 4 components of the climate system. So in addition to the well-known physical laws obeyed by these different components, we also have to do a lot of parameterization of the processes that we don't resolve explicitly in our climate models. And this is where it becomes a bit of an art, I think, to building our models, and leads to differences between different models in the ways that they are parameterized on the subgrid scale processes. So typically our numerical models of the climate system, maybe a couple of years ago, typical resolution was 200 kilometers in a grid box. So we're not going to resolve New York City in our global climate models, but maybe we can resolve a quarter of the state of New York or something like that. And now the new models are emerging where we can actually run them at a much finer resolution, say 10 kilometers. And this affords us the possibility of resolving much higher impact events, weather events such as hurricanes. I believe Carrie Emanuel gave a talk here in this series. So we're almost at the state now where we can have long enough and reliable enough models at the global models at the 10-kilometer resolution to make these projections. What I'm going to be showing you today are based on a model with this coarser resolution to it. So what we do are to conduct simulations of both the past, which is very important, these retrospective simulations with which we can compare our observations as a way of validating the models. And then we also conduct simulations of the future. And we do this by specifying the known or estimated external radiative forcings. For example, volcanoes, greenhouse gases, sulfate aerosols, etc. And the important point to note here is that we're not asking our models to replicate the observed sequence of variability that we have seen in nature in our retrospective simulations. Because these, the sequence of the free component of variability is not tied to any particular year or forcing for that year. So for example, if in the real world there's an El Nino event in 1982, in 1987, etc., the model doesn't have to produce El Nino events in those years. All it has to do is to replicate the overall statistics, the statistical distributions of the variability. But we don't need, our models don't need to replicate the exact timing of these phenomena. And I think sometimes that's sort of a misunderstood aspect of our climate models. So that's an important factor. And then, of course, the challenge in terms of validating our models, and of course this is a very large subject, is then how do we actually evaluate how good our models are. And of course, if we're going to evaluate the statistics of climate variability, we would like to have long observational records to do that with. And that's really not the case. We have at most about 100 years of observational data worldwide with which to evaluate our models. And this is really not enough to really pin down the decadal variability. So this is still an area, I think, of research that deserves a lot more attention by the statisticians of how best to use our limited observational record to assess our climate models. Okay, so on to some of the experiments that we've run at NCAR with the NCAR community model. This is, again, one of these comprehensive climate models that is housed at NCAR, but it's drawn from efforts by a very, very large number of universities and institutions. So here what we've done is to run, most modeling centers, I should say, just run one simulation of the future, so one possible trajectory of future climate. And here we actually decided to run a lot. We ended up with 40 just as a balance of computer resources and length of each of these runs. But we ran 40 simulations of the first half of the 21st century. And we were interested in seeing how much these different simulations diverged over time. Because of course that gives us sort of the spread or in our ability to predict future climate. So the important thing here is that each one of these simulations, which covers, each one covers the 60-year period, each one of these undergoes the identical external radiative forcing that is specified to the model. So we specify the same increase in the greenhouse gases, the same changes in the sulfate aerosols, black carbon, concentrations, solar variability, and some other ozone, stratospheric ozone amounts, etc. But each of these, of course, is free to evolve along with having this external forcing specified. So each of these 40 that was done for the 20th century, so the model is in rough equilibrium with the external forcing that was applied throughout the 20th century. And then in January of the year 2000, we begin all of our simulations. And the only difference amongst the way that we began these simulations, these runs, are small changes to the initial conditions in the atmosphere. So this is akin to the Lorentz butterfly effect, if you will. These are very small, almost round-off error in the atmospheric initial conditions. So small perturbations, and we're just going to see to what extent the different simulations diverge over time. And then, of course, by definition, the spread of these simulations over time is unpredictable. That's what we're testing here. So they all begin with the same ocean initial state, the same change in the external forcing, small perturbations just to the atmospheric initial conditions. So this is a picture of what might happen if this model is a good one, a realistic one, to future air temperatures over North America during the wintertime. And I'll explain what's plotted here. So what we've done is we take this 50-year record from 2010 to 2060, so the next 50 years, and at each grid point in the model, we simply fit a linear trend to the evolving time series. And then we're just plotting the magnitude of that trend. So think of that as the change or over time in the near surface air temperatures over North America. And I'm showing you two contrasting simulations from the set of 40 that we did, just to make a point here. And both of these, of course, are undergoing the same increase in the greenhouse gas concentrations, but they give very different outcomes for future climate. So, for example, this particular run, number 16, it has no significance to the number, we actually find slight cooling over the southeast U.S., despite that the greenhouse gas concentrations are increasing. And in contrast, number 22 gives us a much warmer future, much stronger warming, particularly over the high latitudes, but also for the U.S. as a whole. So these numbers here are the average warming trend for the average over the contiguous United States. So in the top plot, the U.S. as a whole here warms by only 0.8 degrees C, whereas in this run, if we average over the contiguous U.S., we get a warming of 3.4 degrees C. So quite a different outcome. And it's with the same model, remember, and these are not predictable because of the way that the experiment was set up.
Excuse me.
Yes, sure.
Sorry. Is this in one particular year, for example, 2059, or average?
So thank you for that question. So what we did was we can just, for example, take a point here in Texas. And the model gives us the daily temperature record from all the months from 2010 through to 2060. So we have a 50-year record of the daily temperatures. And then all we do is fit a linear regression, and we're plotting the slope of that. So it's not a particular year, it's not a particular decade. We're saying what is the overall rate of warming, linear rate of warming at each location. So that's what the colors signify. So the color bar here is the change in the temperature in degrees Celsius over this 51-year period. Okay. So now I'm coming back to some of the conceptual points I made at the beginning of the talk. So, of course, as we have already talked about, each single realization, if you will, of this climate model contains a mix of the forced climate change signal and the free variability. Now, in the model world, it's very simple to decompose this because to get at what was the component that's externally forced, we just have to do an average over all of the 40 runs, assuming that the free climate variability is randomly sequenced across the 40 runs. We reduce the random free component of the trend, and we're left with an estimate of the forced component. And then if we subtract the forced component from the total trend, then we're estimating the free component. In the real world, you can't do this. You don't have 40 runs of nature. And we'll talk about near the end of the talk how one might start to estimate what is forced, externally forced, and what is internal to the climate system. So let me illustrate then this decomposition for each of these two runs. So on the left are these the two rates of change of temperature over the next 50 years according to this model. And then we show the decomposition. So on the far right, that is the part of the rate of temperature change that is, by definition, a result of the specified external radiative forcing. And I'm just using greenhouse gases as the primary forcing over this time period. So if you just look at the right-hand maps, which of course are the same in the two rows here, you see a very canonical signature where we have more warming in Canada than over the US. And this is a signature of the poleward amplification that has been known for a long, long time, especially in the wintertime, a tendency for more warming at the surface in the higher polar latitudes compared to lower latitudes. Then, as I said before, if we subtract the forced rate of change of temperature from the total, we're left by definition with the free component. And so here is, I think, a very interesting visual description then of these two parts of the total rate of change. So for the U.S. as a whole, the increase in the greenhouse gases gives us something like 2 degrees of warming over the next 50 years. And in this particular run, the free component offsets that by about 50%. And in fact, much of North America, except for the very highest latitudes, actually show cooling due to the free component of the variability, or the rate of change here. And then conversely, if we look at the run that had a lot of warming over the US, you can see that the free component of the warming is augmenting the forced component by substantially, by about 50%. So the important thing here, there are 2 important points. One is that the free component of the internally generated component of 50-year climate trends can have amplitudes that are rivaling those due to the greenhouse gas forcing over the next 50 years over North America. And the other important point is that the free component of the rate of change is not, it has large spatial scales. So it's not a matter of, one state gaining and one state losing. It's really the whole very broad region of the U.S. can have the same sign of the free variability. So of course this has important implications for how we manage our resources. It's not a zero-sum game. It's a change to the whole continental U.S. So let me give you now another example. Let's look at the rainfall changes in the summertime. And here we see even more disparate looking outcomes from the climate model. And believe me, when we first got these results, we really had to make sure we hadn't done the experiments wrong, but I assure you we didn't. So on the right-hand side now, I've picked out the 2 contrasting runs. And for the summertime rainfall change, and the scale here, you don't have to pay too much attention to the units, but just note that the brown colors signify a drier future, and the greens and blues signify a wetter future. So you can see that for much of the central U.S., in fact, you can have completely opposite polarity of these future summer rainfall trends. And the U.S. averages, contiguous U.S. averages are given here. And then finally, we can do the same decomposition that we did for the wintertime air temperature. We can do this for the summer precipitation trends. So you just saw the maps on the left, and then we can average all of the 40 realizations from this single climate model, and those are the maps on the right. So most areas are indicating a wetter future. But you can see now that the forced component of the change, particularly over the contiguous U.S., is in fact smaller for these examples than the free component. And you can see here from these numbers that the forced component is only something like 1/3 as large as the forced component. So that's suggesting that it's going to be actually very difficult to tease out in the real world, if the real world is, going to be one of these runs, going to be difficult to tease out the component of future changes that are externally forced. So one other thing, one other way to look at this information then is to just kind of do the very simplest thing, and just to count up at each grid box, count up the number of simulations that showed a positive trend, and then divide by 40, the total number. So giving us a chance of having either a warming trend or a wetter future. So that's kind of like the lowest common denominator. We're not asking how warm is it going to get or how wet. We're just saying what are the chances that it's going to get warmer or wetter. So here are the results for trends over the next 50 years, so rates of change over the next 50 years. These examples are for the wintertime with precipitation on the left and temperature on the right. So we can start with the temperature, and you can see that it's nearly guaranteed, according to this climate model, that we will have warming. But, of course, much more uncertain is the magnitude of the warming, and that's what I showed you in the last couple of slides. For precipitation, for a large part of the eastern portion of the country, we're kind of in this even chance coin flip zone in the green colors here. Although there are areas where there are, higher probability of having a drying trend compared to a wetting trend. And then, of course, for northern Canada and Alaska in the wintertime, high chances.
A negative trend means less rain.
That's right. So that's why I've written it here. The blue colors, you can interpret it as a high chance of less rain. Yes, a high chance of less rain. Exactly. So the U.S. as a whole, if we look at it that way, we're sort of near even chances here. So this is over the next 50 years. What about if we do the same thing for rates of change in the near term? Just cut our sample, our time horizon in two, and look at the next 25 years. So in the next 25 years, according to this model, what are the chances of having that it will be warmer or wetter? So we can start with precipitation, and just to note a lot of green colors. So we're in this zone where the natural variability is commensurate with the forced signal. And so there really is not, obviously, a big forced component. And the temperature, on the temperature side now, you see large areas of the U.S. that have chances that are more in the 65-75% category. So don't be surprised if, where you live, if it hasn't gotten warmer, or if you're expecting it to get wetter and it hasn't. That doesn't mean that climate change, externally forced climate change, isn't happening. It just means that that part is small compared to the natural climate variability on this shorter time scale. So I have a few more ways to illustrate the results, and then I'll get onto some of the challenges. So here's another sort of fleshing out the picture a little bit, coming back to the summertime and coming back to the air temperature. And again, rates of change of air temperature over the next 50 years. And so here, the run A and B are the two most contrasting simulations from this model. So A is giving you, we picked out the run that had the warmest future for the contiguous U.S., and run B had the least warming of all of the 40 runs. And so, for example, we can get increases in temperature in run A that are between 4 and 5 degrees, whereas run B, you'd only be warming by, less than a degree. Then the top picture is the average of all of the 40 runs. So to the extent that the variability, the free variability, is randomly sequenced amongst the 40 runs, this gives us an estimate of the externally forced signal. And this is sort of the maps that we're used to seeing and used to thinking that this is what nature will give us. But nature will not probably give us the average. It will give us some, single realization. And that, if this model is any guide, that realization will sit somewhere between these two. Then what we have here is, I'll just go through this bunch of records, time histories of the air temperatures at particular regions or locations. So the black curves, starting back in 1910, these are the observed temperatures from standard observational data sets. And then the blue and the red curves that are then matched, that depict the future conditions, these are taking the two runs that had the biggest differences for each location. So let me go through that. So this global curve here, that's the air temperature over all land regions of the globe. And the black line again is the observed record, and you can see it's starting to warm in the last few decades. And then the model says, okay, that warming is going to continue, and the uncertainty in the rate of warming due to the free component of climate variability is quite small. These are quite similar in terms of their rates of warming. Then we can look at the same picture now averaged for the contiguous United States, and now you can see more spread in the rate of future warming. And by the way, these gray bars are giving you the histograms, the distributions, to show you the rates of warming from all 40 runs, so you can get some sense of the overall spread amongst the 40 members. Then we have Canada. Again, two different rates of warming, and then we picked out for this presentation the grid box. It's not New York City precisely; it's the grid box that contains New York. And again, there's been warming and periods of higher temperatures and periods of cooler temperatures in the past, in the recorded past. And then, according to this model, somewhere warming will continue. But the rate of warming could be somewhere between 1.5 degrees and maybe 3 degrees. So maybe a spread of a factor of 2 in the amount of warming as a result of the superposition of the forced and the free components of the trends. And then finally, boil it down into this histogram here. These are the results for the wintertime temperature trends for, again, the New York City grid box, Canada as a whole, the contiguous U.S., and then the global land areas. So these numbers are the rates of change over the next 50 years, and you can see that there's quite a spread from near zero to almost 4 degrees for the New York City grid box. Canada also has sizable spread, as does the U.S., and then the globe is much more truly global warming.
You said the rate of change. You mean the total change?
I mean the total change. Thank you. Yes.
Right.
Yes. Yes. The total change over these
4
50
degrees
years.
a year would be quite a rate.
Yes. It's the rate of change over the full 51 years, exactly. And so this, again, is, according to these experiments, this is by definition not predictable. We began with the same ocean initial state and just very small perturbations to the initial atmospheric state. And then the climate system, each of these runs diverged considerably. So now I'd like to just discuss briefly some of the proximate causes for the spread amongst these simulations. And I want to point out the role of of the atmospheric circulation in governing not only the amplitude of the variability, but the large-scale spatial patterns of the free component of the variability. And so again, I'm just giving you illustrative examples to make the point. So here are another 2 of the 40 runs. I haven't shown you this before. And again, the colors we've been looking at are the air temperature changes over the full 51 years in the wintertime. And then the black contours, the solid and the dashed contours, are the sea level pressure, the barometric pressure linear trends for these 2 particular runs. And the solid contours signify an increase in the barometric pressure over time, and the dashed contours signify a decrease in the barometric pressure. So I picked these 2 runs to make the point that you can get, equal and opposite changes in the atmospheric circulation over the next 50 years, i.e. the forced component of the response in the circulation is small compared to the natural variability. And we know from, very simple reasoning and many, many years of experience that the changes in the flow patterns associated with gradients in the sea level pressure field will change the flow of air masses and give us different changes in the air temperatures. So for example, when we have this strong high over the Pacific, that's going to tend to bring cold air down from the north and cool the land areas. And when we have a strong low pressure in the Pacific, we're going to tend to bring up warm maritime air from the south and warm the adjacent land regions. So let me do the same decomposition of both the temperature and the atmospheric circulation into the forced and unforced components. And so now you can see very, very clearly, if we just pay attention to the middle column, this is the free component of the trends in these 2 particular members of the ensemble. And here you can see that most of Canada is, in the top middle figure, is cooler, and that's a result of, qualitatively speaking, a result of the enhanced winds coming down from the north. Whereas in the middle, in the lower middle panel, you can see that much of the western part of North America is warmed as a result of the prevailing winds from the south. And then again, it makes the point as well that the forced component of the circulation change is small compared to the unforced, or the free component of the circulation change. So a way that I think we can move forward interpreting what is forced and what is unforced is to take into account the impact of these circulation trends on the air temperature, and then to account for them and then to subtract them, if you will. So what we've done is to take our long control runs of the model. So we have no changes in the external forcing whatsoever. So we're just sampling the free component of variability. And then we look at the relationship between when the winds are in a particular direction, what the temperature is doing at each grid point. So if we find very simple relationships, if the winds are from the south, there's warming at a particular grid point. And so we build up this knowledge of the impact of the circulation on the temperature in the free variability of our control run. And then we just use this mapping to then project these trends and to remove the impact of the circulation. So it's sort of a poor man's way of assessing the thermodynamic effect of the circulation on the trends. So I'll show you the result here. So again, on the left, these are the original trend maps for these two particular ensemble members. And then we remove the component of the temperature change that was induced by the free part of the circulation change, if you follow me. And now you can see that the two runs are actually very similar. And that's because the thermodynamic component of the warming is mainly a forced signal, and the circulation-induced component of the temperature change is mainly a free signal of the free variability. So I think that this is a useful way then of comparing single runs from different models, and also, as I will show you next, it helps us to interpret what we have observed in the recent past. And I'll end here with one example of how I think this may be useful for the interpretation of climate trends that we've already observed. So here is the example. So now for the first time, or maybe the second time in this talk, we're looking at actual observations. And here we're looking at this 35-year period since starting in 1970 to 2005. Again, looking at the linear rate of change of temperature at each location over North America, and then looking at the change in the sea level pressure field, the indicator of the atmospheric circulation. So we've, in the wintertime, we've had a lot of warming, especially at the higher latitudes of North America, and we've had a tendency for lower pressure pressure falls over the North Pacific, and you can, so that's what the real world has done. So we have another set of large number of simulations of our climate model for this time period. We have a 30-member set of simulations. And again, I'm picking out contrasting runs just to make the point obvious. So let me show you run A and run B from this 30 members. And I picked run A because it looked a lot like the observed change. In other words, a lot of warming, particularly more warming in the north than in the south, and then lower pressure, trends of lower pressure over the North Pacific. So you might think, if that's the only run you had from your climate model, A, that your climate model was doing a great job, and B, that, wow, external forcing has, lowered the pressures in the North Pacific and changed the temperatures in this fashion. But then if you ran the model again, you might get run B. And lo and behold, run B tells you that actually, no, it was cooling over Alaska and northern western Canada, and warming a lot in the southeast, and the pressures actually increased over the North Pacific and fell over much of the U.S. And of course, you wouldn't be able to make any of those conclusions. So here, I've applied the same approach, the same methodology of accounting for how the circulation trends have impacted the temperature trends. And then I remove that effect, and I see what is left. So that's what I'm going to show you here. And we've done this both on the observations and on the individual model runs. And now you can see that the two model runs are, of course, they're not in precise agreement, but they're in much better agreement with each other after accounting for the impact of the different circulation trends. And the observations are closer to these model runs as well. So this is a way of getting at the radiatively forced component of the warming over North America and removing the impact of the free component of the circulation trends. So I think this is very important for how we interpret our observational records. Just because it's been warming a lot in Canada, not all of the warming is actually a result of increased greenhouse gases. Some of it was actually due to changes in circulation, which could have been a result of the external forcing. But as I showed you from these model runs, the externally forced component of the circulation changes is small compared to the natural variability. So I'd like to apply that same reasoning then to the observations. So what I've shown you is the type of spread that should be expected from this particular climate model for trends, 50-year trends into the future as simulated by this model. And I've shown you that in some cases, particularly for precipitation, the uncertainty of our projections for the next few decades is large relative to the force signal as a result of the free climate variability. So are there any prospects for narrowing this uncertainty? And then here we come to, I'd say, a research frontier for climate science, and where the focus is on doing so-called initialized decadal predictions. So the overall concept is that the oceans, with their vast thermal inertia, will contain some predictable component over the next, let's say, decade probably at most. And that will have some impact on the adjacent climate over the adjacent continents. So people are just starting to, first of all, we need to have very good observations of our ocean state. That's the first challenge in this decadal prediction. And then once we have that, we feed that into our climate models and look at the evolution of the system. So it's different from the experiments that I showed you, where we began from the model's ocean initial state that could be very different from the observed one at any particular time. Here we're saying, okay, I know the ocean is in this particular phase of a decadal cycle, and what does this give us any added predictability? And as I say, this is very much a research frontier. I'm not involved in the research, but there are some papers that are just starting to come out on this. And I'll just remind you of these, what we consider to be the two main phenomena, if you will, of multi-decadal variability in the oceans. On the left, again, is this Atlantic component of the ocean thermohaline circulation, which, again, you've seen this curve before, exhibits variability on decadal and multi-decadal timescales. And then the other important phenomenon is the specific decadal variability, which also exhibits long timescales. And of course, our observational records are much too short to assess whether these are cyclical phenomena or just sort of a red noise continuum. We just don't have enough samples to answer that question. And it's particularly important to note that these time series, although they look fairly regular, the decorrelation time scales is only about 10 years. And beyond that, you can consider them, sort of random stochastic processes. So really, we shouldn't expect much predictability beyond this 10-year time scale. And I'll finish up here with showing you this figure that I believe was shown in the last lecture, yes. Brian Soden. And so this is a picture, of course, that's been making the rounds from The Economist and discussing this recent period of about a decade where global air temperatures have not risen according to expectations. But our expectations are that we are going to see the forced component. And I've been trying to really warn us, caution us, that that's not the only thing going on. And in fact, again, it's a research frontier, but the paper by Meal et al., which does these initialized decadal predictions, they're suggesting, and I think we'll have to see if other research bears this out, but that the particular phase of this tropical Pacific decadal variability actually had an impact, was causal to this global warming hiatus. And if you notice here, the first part of the record from 1950 to the 1970s, when we had cold ocean temperatures in the tropical Pacific, we didn't have much warming at all. Then when the tropical Pacific warmed rapidly, we had a rapid change in the global temperatures. And now we've been in a cold phase of this Pacific decadal variability for the past 10 years or so. And that's coincident with this hiatus in the global warming signal, global temperature warming signal. So again, from their work with the initialized decadal predictions, and based on our models, which are of course not the real world, they're suggesting that this can't last more than another 5 years or so, at least if our models give any precedence. So the ongoing challenges in terms of narrowing the uncertainty in future projections really rests on, I'd say, three main areas. One is that we base our projections on our numerical climate models, and there is much scope for improving these models. And this is a very significant challenge to improve not only the physics in the models, but the parameterizations that we have to make, increasing the spatial and vertical resolution and numerical methods in these models. Then I think, as I alluded to before, we have to have clever ways to evaluate our models given the limited duration of our observational records. We can only evaluate climate variability in the models in a sort of probabilistic sense because we can't, the sequence, the exact chronology of the free variability doesn't have to match that seen in nature. And then finally, this all requires substantial advance and increase in our computational resources. And I think I will just thank you very much for your attention.